Hi guys, today we're going to talk about Chapter 10 Math 1C. Our group member is consisted of Tan Pham, Minqi Zhou, Arya Suprana, Qiqi Liang, Weicheng Huang, Mingming Tan, Jue Luo, Se Kai, and Kenny Suryadinata. In this chapter, we will review some of the materials from pre-calculus, geometry, and calculus. We will look at three different coordinates: rectangular coordinates, parametric coordinates, and polar coordinates, plus two linear operators, which is differentiation and integration.
Let's start with arc length. Arc length finds the length of the function from one point to another point. To find the general form, let's look at the graph of the function f of x and then try to find the arc length from point P to point Q. If we were to draw a straight line from P to Q and form a triangle, the length from P to Q would be equal to the square root of delta x squared plus delta y squared. However, this would cause the error to be large. Instead, we could find the arc length by drawing smaller triangles and finding the integral from a to b of the square root of delta x squared plus delta y squared. Let's start with L equals the integral from a to b of the square root of delta x squared plus delta y squared. For rectangular functions, delta x and delta y are the same as writing dx and dy. Plug these quantities into the equation and you get that L equals the integral from a to b of the square root of dx squared plus dy squared. Then we simply pull out dx squared from the square root and get that L equals the integral from a to b of the square root of 1 plus dy over dx squared dx. dy over dx is the same as the derivative of the function, or f prime of x. This means that the arc length is then equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. We now know how to find arc length of a rectangular function, so let's move on to see how to find the arc length of a parametric function. We know that arc length is equal to the integral from a to b of the square root of delta x squared plus delta y squared, which we could then change to dx and dy like we did for rectangular functions. However, in parametric functions, both x and y are functions of t. Now, to change dx and dy into terms of dt, we can multiply and divide by dt to change arc length to the integral from t1 to t2 of the square root of dx over dt squared plus dy over dt squared dt. dx over dt and dy over dt can be rewritten as x dot and y dot, giving the final equation to be the integral from t1 to t2 of the square root of x dot squared plus y dot squared dt. For polar functions, we will start with arc length is equal to the integral from a to b of the square root of delta x squared plus delta y squared, which we can change to dx and dy. Since we are in a polar coordinate system, x and y are in terms of theta. To change dx and dy into terms of d theta, we need to multiply and divide by d theta to give the integral from theta 1 to theta 2 of the square root of dx over d theta squared plus dy over d theta squared d theta. We also know that in a polar coordinate system, x is equal to r cosine theta and y is equal to r sine theta. Taking the derivatives of each, we get that dx is equal to dr cosine theta minus r sine theta d theta, and dy is equal to dr sine theta plus r cosine theta d theta. If we divide both sides by d theta for each equation, we get that dx over d theta is equal to dr over d theta cosine theta minus r sine theta, and that dy over d theta is equal to dr over d theta sine theta plus r cosine theta. To match what we have under the square root, we will square dx over d theta and dy over d theta, which will give us that dx over d theta squared is equal to r prime squared cosine squared theta minus 2r r prime sine theta cosine theta plus r squared sine squared theta, and that dy over d theta squared is equal to r prime squared sine squared theta plus 2r r prime sine theta cosine theta plus r squared cosine squared theta. If we add these two quantities, we get that dx over d theta squared plus dy over d theta squared is equal to r prime squared plus r squared. This gives us the final equation that arc length is equal to the integral of theta 1 to theta 2 of the square root of r prime squared plus r squared d theta.
In a three-dimensional coordinates, we have the parametric function equation of the arc length of a function becomes integral from t1 to t2 of root of x dot square plus y dot square plus z dot square dt. You see, in a 3D coordinates, we have one more coordinate, which is the z coordinates, which is why the equation form change into this form. Also, in the rectangular coordinates, the equation becomes s equals to integral from x1 to x2 of root of 1 plus y prime square plus z prime square dx.
Now let's talk about surface area. Let's imagine the following function rotated around the horizontal axis. What would be the resulting surface area? Since we are in Calculus 1b, we will start by taking a segment. This segment will be the radius of the small circle that we formed. The circumference of this circle is then equivalent to a section of the total surface area. However, if we zoom in on the section, we see that just multiplying the circumference by dx would have a lot of error. Instead, we need to multiply each circumference by arc length to get the most accurate measurement. If we rotate around the x-axis, the radius of the circle would be y, which means that for this segment of the surface area, we would multiply 2 pi y by the arc length. The same is true for when we rotate around the y-axis. The new radius would be x, so the segment of the surface area would be equal to 2 pi x times the arc length. So, for rectangular functions, the surface area would either be equal to the integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx, or the integral from a to b of 2 pi x times the square root of 1 plus f prime of x squared dx, depending on how the function is rotated. For parametric functions, x and y are in terms of t, so the surface area would then be equal to the integral from t1 to t2 of 2 pi y of t times the square root of x dot squared plus y dot squared dt, or to the integral of from t1 to t2 of 2 pi x of t times the square root of x dot squared plus y dot squared dt. Finally, in polar functions, y is equal to r sine theta and x is equal to r cosine theta. So the surface area is equal to the integral from theta 1 to theta 2 of 2 pi r sine theta times the square root of r prime squared plus r squared d theta, or the integral from theta 1 to theta 2 of 2 pi r cosine theta times the square root of r prime squared plus r squared d theta.
For the first example, for surface area of a rectangular function, we are going to use this function here, which is y equals to x, and we're going to rotate it around x-axis. Now, since we are going to rotate it around x-axis, the surface area formula will be integration from a to b of 2 pi y times the arc length, which is 1 plus dy over dx squared dx. Now let's see here. dy over dx will equal to 1 because y equals to x. And surface area, the formula becomes integral from 0 to 1 because we're going from 0 to 1 here of 2 pi. Since y equal to x, we can rewrite y as x root of 1 plus 1 square dx. 1 plus 1 square and 2 pi are, this thing here and 2 pi are both constant, so we can move it out of the integral, and it becomes 2 pi times root 2 times integral from 0 to 1 of x dx. And then it becomes 2 pi root 2 x squared over 2 from 0 to 1. And the answer is 2 pi root 2 over 2, and the 2 crosses each other, minus 0, which is pi times root 2. Okay, so for the second example for rectangular function surface area, we are still going to use the previous function, which is y equals to x, but now instead of rotating around x-axis, we're going to rotate it around y-axis. Okay, I believe that in the previous slides, we made a mistake because the surface area of a rectangular function when it is rotated around y-axis is not just integration from a to b of x times 1 plus dy over dx squared dx, but we have to rewrite the x in terms of as a function of y, so we have to write it as integration from a to b of x as a function of y times the arc length. And because we are doing it in terms of a function of y, we have to use dy here, and we change the dy over dx into dx over dy squared plus 1. And then because this is a function of y, a and b, the limit of integration here, represents the range from where y goes from to where y goes from. In this particular problem though, the limit of integration will still be the same because at x equals to 0, y equals to 0, and x equals to 1, y equals to 1 too. Let's rewrite this entire thing. So surface area of this problem equals to integration from 0 to 1. Oh, and don't forget 2 pi here. 2 pi. Because this is the circumference of the circle, so you have to time it by 2 pi. 2 pi. Okay, so from 0 to 1 of x of y, in this case x of y equals to y, times 1 plus, and dx over dy equals to 1, so 1 squared. It equals to 1 because y equals to 1, yeah, and times dy. Now we can move this entire root here out because this is a constant, and it becomes 2 pi root 2 of integration from 0 to 1 of y dy, and this becomes 2 pi root 2 of y squared over 2 from y equal to 0 to y equal to 1, and the entire thing becomes 2 pi root 2 over 2 minus 0, which equals to pi root 2. So the first example that we are going to use for surface area of a parametric function is the parametric function xt equals to t and yt equals to t squared from t equals to 1 to t equals to 2. And for this first example, we are going to rotate this entire parametric function around the x-axis. Therefore, as we just learned, SA equals to integration from t1 to t2 of yt times the arc length, which is x dot square plus y dot square dt, and the entire thing times 2 pi. Now let's rewrite this in this problem. In this problem, yt equals to t squared. Therefore, SA equals to 2 pi integration from t1 to t2 of t squared times the root of, and x dot here equals to 1 because xt equals to t, so x dot equals to 1, and y dot equals to 2t. So the thing under the root becomes 1 plus 4t squared dt. From here, we can just substitute using trigonometric substitution and let 4t squared equals to tangent theta, and then we can solve this. Maybe using integration by parts in the middle, and then we can go on and get the answer. Now for the second example for surface area of a parametric function, we are still going to use the same parametric equation, which is this, xt equals to t and yt equals to t squared, but this time we are going to rotate it around y-axis. So the surface area formula changed a bit. SA equals to integration from t1 to t2 of, instead of yt, this time it's xt because we are rotating it around y-axis, and the x becomes the radius, times 2 pi times the arc length. And the arc length for a parametric function is x dot square plus y dot square dt. In this particular problem, x dot equals to 1 and y dot equals to 2t. Therefore, we can rewrite the entire surface area formula into SA equals to 2 pi times integration from 1 to 2 of xt, which equals to t times root of 1 plus 4t squared dt. Now this is just a very simple u substitution problem. You can just let u equal to 1 plus 4t squared and du equals to 8t, and then just multiply this by 8 divided by 8, and then the t and dt will become du, and it becomes a very simple integration. Okay, so the first example that we are going to do for surface area of a polar function is this function, polar function, r equal to 2 sine theta. Now, in this first example, we are going to rotate the entire function around x-axis, which is why the radius will be the y of this function. So SA equal to 2 pi times integral from theta 1 to theta 2 of, because the y of a polar function equals to r sine theta, so we write it as r sine theta, times the arc length. The arc length equals to r prime square plus r square d theta. Okay, let's substitute in what we know here. R equals to 2 sine theta, and then r prime equals to 2 cosine theta. That's pretty much all we need to know. So we can rewrite this as SA equals to 2 pi times integral from 0 to pi over 3, which is right here, times r sine theta. And since r is 2 sine theta, we can rewrite it as 2 sine square theta times root of 4 cosine square theta plus 4 sine square theta. And this entire thing under the root becomes root 4, which is 2. And we can combine the 2 of the root here and the 2 here and move it outside with the 2 here, and they all becomes 8 pi times integral from 0 to pi over 2 of sine square theta d theta. Here too, don't forget the d theta, it's very important. Now, with sine square theta or cosine square theta, we know that we have to change them into cosine 2 theta, in terms of cosine 2 theta. Therefore, we can change this into 4 pi, because I know there will be 1/2, and I just put the 1/2 out right away, times integral from 0 to pi over 2 of 1 minus cosine 2 theta d theta. And then you can just go from here. It's a very easy integration from here on. For the second example of polar function surface area, we are going to use the same polar function, which is r equal to 2 sine theta, but this time we are going to rotate it around y-axis. Now, the formula for surface area, if we rotate around y-axis, we have to time the radius, and the radius becomes the x of the function, and the x of a polar function equals to r cosine theta. So it becomes integral from theta 1 to theta 2 of r cosine theta times the arc length, which is root of r prime squared plus r squared d theta. And don't forget to times 2 pi, because we are trying to look for the circumference of the circle of a segment. Now let's substitute what we know from the problem. We know that r equals to 2 sine theta. So r prime equals to 2 cosine theta. So SA equals to 2 pi from integral from 0 to pi over 3 of r. We can change r into 2 sine theta. So 2 sine theta cosine theta root of 4 cosine square theta plus 4 sine square theta, which equals to 4. So d theta, don't forget d theta. So we can move the 4 and the 2 out. Well, the 4 is within a root, so it becomes 2. So it all becomes 8 pi times integral from 0 to pi over 3 of sine cosine sine theta cosine theta d theta. And we can just use u substitution and let sine equals to u, and it becomes a very, very simple integration. Trochoids. There are three types of trochoids. The first one is called curtate trochoid. The second one is called common trochoid, also known as cycloid. And the third one is prolate trochoid. When we have two-dimensional wheel rotating on a two-dimensional path, each point on that wheel will have a similar path. These paths created by the rotation of the two-dimensional wheel are called trochoid. Let's look at this picture in the slide. The first one is curtate trochoid, is when the point that we choose is inside the two-dimensional wheel. The second one, cycloid or common trochoid, is when the point that we choose is on the edge of the two-dimensional wheel. The third one, the prolate trochoid, is when the point that we choose is outside of the two-dimensional wheel. So we can see the difference. The curtate trochoid makes a smaller path, while the prolate trochoid makes the longest path. Now, how do we find the parametric equation for cycloid? First of all the equations that we are going to prove in this presentation will assume that the point we choose on the two-dimensional wheel starts from the origin. Let's look at the picture here. This is a picture of the two-dimensional wheel where the cycloid starts from 0.0. So the cycloid will look like something like this. So this point here is going to be the point that we are examining. Now we can see that the arch PB equals to OB. And OB, which equals to the arch PB, equals to A times theta, because that's how you find the circumference of a circle. Because of that, we know that the x of this point equals to A theta, which equals to OB minus this length here, which is A times sine theta. And y theta equals to A, which is this length here, minus this length here, which equals to A cosine theta. Next, we have the curtate trochoid. In a curtate trochoid, as I explained before, we choose a point that is inside the two-dimensional wheel, which is why it makes this kind of path right here that I have drawn. So let's look at it. In here also, PB equals to OB. The arch PB, which is the one that I'm highlighting right now, is equal to the length of O to B. You have to agree with that. And the arch PB equals to A which is the radius of the circle, times theta. Again, it is how you find the circumference of the circle. With that known, we know that the x of this point, which is the point that we are following, the x here equals to OB minus the base of this small triangle right here. And the base of that small triangle equals to sine theta times the length of this. But the length of that equals to the radius of the circle minus the length of this part, which is h. So we have x theta equals to a theta minus a minus h times sine theta. And the y theta, which is from here to here, equals to the entire length of this radius, which is a, minus the cosine of the same triangle. So it becomes a minus h times cosine theta.
In this slide, we're going to find the parametric equation. So first of all, let us start with x theta. From the picture, we know that x theta equals OB plus BC. From the previous slide, we already know that OB equals r plus small r cosine theta, and BC equals small r sine the angle of BAP, which is alpha plus theta minus 90 degrees. And then it equals r plus small r cosine theta plus small r cosine alpha plus theta. And then it equals r plus small r cosine theta plus small r cosine. So here we change the alpha to r theta over r, as we already know from the previous slide. So it becomes small r cosine r theta over small r plus theta. And then we finally find that the x theta equals r plus small r cosine theta plus small r cosine r plus small r over small r times theta. So now we're going to find the y theta. From the picture, we know that y theta equals AB minus CP. We know that AB equals r plus small r sine theta and CP equals small r cos the angle of BAP, which is alpha plus theta minus 90 degrees. And then it equals r plus small r sine theta plus small r sine alpha plus theta. And then it equals r plus small r sine theta plus small r sine alpha, which is r theta over small r plus theta. And finally, we found that y theta equals r plus small r sine theta plus small r sine r plus small r over small r times theta. So finally, we find the parametric equations. So x theta equals r plus small r cosine theta plus small r cosine r plus small r over r times theta. And y theta equals r plus small r sine theta plus small r sine r plus small r over r times theta. So now it is hypotrochoid. The rotating wheel is inside of the other wheel. As the picture shows that the curve PQ equals the curve QA. And we know from the picture that curve PQ equals small r times theta plus alpha, and curve QA equals r theta. And then it becomes small r theta plus small r alpha equals r theta. And then we move the small r theta to the right side, and then it becomes small r alpha equals r minus small r times theta. And then we finally find that alpha equals r minus small r over small r times theta. In these slides, we are going to find the parametric equations. So first, we'll start with xt. From the picture, we know that xt equals r minus small r cosine theta plus small r cosine alpha. So xt equals r minus small r cosine theta plus small r cosine r minus small r over small r times theta. And then now we're going to find the yt. From the picture, we know that yt equals r minus small r sine theta plus small r sine alpha. So yt equals r minus r sine theta plus small r sine r minus small r over small r times theta. So finally, we find the parametric equations. So x theta equals r minus small r cosine theta plus small r cosine r minus small r over small r times theta. Y theta equals r minus small r sine theta minus small r sine r minus small r over small r times theta. So now here is the questions. When a plane crosses a double cones connected at their vertex, it traces the graph of conics such as ellipse, parabola, and hyperbola. So now find a relation between the eccentricity and the angle of the plane with horizon. So in triangle OAB and triangle ODC in this picture, we know that angle COD equals angle BOA equals theta. And then we let angle OAB equals 45 degrees. And then angle ODC equals 180 degrees minus 45 degrees, which is 135 degrees. And then angle OCD equals 45 degrees minus theta. And angle OBA equals 135 degrees minus theta. So in triangle OAB, we are using the law of sines. So sine 45 degrees over S equals sine of 135 degrees minus theta over R. So it becomes sine 135 degrees cosine theta minus cosine 135 degrees sine theta. So it becomes root of 2R over 2S. So root of 2 over 2 cosine theta minus root of 2 over 2 sine theta equals root of 2r over 2s. From this equation, we know that it equals cosine theta plus sine theta over r over s. And then we label it as the first equation. So in triangle ODC, we are using again the law of sines. So sine 135 degrees over L equals sine of 45 degrees minus theta over R. So it becomes sine 45 degrees cosine theta minus cosine 45 degrees sine theta equals root of 2R over 2L. So root of 2 over 2 cosine theta minus root of 2 over 2 sine theta equals root of 2r over 2l. So from this equation we know that it equals cosine theta minus sine theta equals r over l. And then we label it as the second equation. So the first equation plus the second equation becomes 2 cosine theta equals RL plus RS over SL. And if we divide the equation by 2, it will become cosine theta equals RL plus RS over 2SL. And if the first equation minus the second equation, it will become 2 sine theta equals RL minus RS over SL. And if we divide it by 2, it will become sine theta equals RL minus RS over 2SL. So tangent theta equals sine theta over cosine theta. As we know from the previous slide that sine theta equals RL minus RS over 2SL, and cosine theta equals RL plus RS over 2SL. So the tangent theta becomes L minus S over L plus S. And then as we know that L equals R plus F and S equals R minus F, so the tangent theta becomes R plus F minus R minus F over R plus F plus R minus F equals 2F over 2R. So finally tangent theta equals F over R.
This marked the end of our presentation. Thank you for listening. Bye bye.